Good day, folks. Here's an exam question based on the chemical equilibrium. Let's cut the chase. 33.6 gram of nitrogen and 24 grams of hydrogen are placed in a 5 cubic decimeter sealed container and react according to the following balance equation until dynamic equilibrium is reached. Now, here's the balance equation. 6.1, it says explain the term dynamic equilibrium. Guys, I always say stick to the exam guideline. And the 6.1 dynamic equilibrium, guys, it is a dynamic equilibrium where the rate of forward reaction is equal to the rate of reverse reaction. Now it says at 573 Kelvin, when equilibrium is reached, there's 5.6 gram of nitrogen gas left in the container. Guys, it's very important to know the statement and understand and analyze the statement, what is happening there. These amounts that we are given here, these are the initial amounts. Very important to take note of that. These two amounts, they are initial. These are the amounts that are available in the reaction chamber. Right, so now we are told this is what is left in the container. This is what remained in the container. This is the amount at equilibrium, right? Now 6.2, it says calculate the concentration of both reactants when the reaction reach equilibrium for the first time, right? 6.2, the first thing before we calculate that, we have to change those masses. 6.2, we have to convert those masses into number of moles. So the initials there, so it's going to be number of moles of nitrogen is equal to mass over molar mass. And then the nitrogen there, it's 33.6 divided by nitrogen, its molar mass, it's 14 times 2. So the answer there, when you punch that in the calculator, it's going to be 1.2 mole. Sorry. And then number of moles of hydrogen, the initial one is the mass, which is the mass, it's 24 gram. And then divide by the molar mass of hydrogen gas, it's 1. Since it's a diatomic, you times by 2, so it's going to be what? 12 mole, right? So doing that, now we have the number of moles. Now at equilibrium, we're told that 5.6 of nitrogen remained. So I'm going to convert that nitrogen that is at equilibrium, which is 5.6 divided by 14 times 2, which is 28. So it's going to be 0.2 mole. So I'm going to take these amounts and insert them in a table. When I insert them in a table, it would give me the amounts that I need, the concentrations at equilibrium as the question requires. So this question, it wants the amounts, the concentration of the reactants, which is the hydrogen and nitrogen at equilibrium for the first time. So what I'm going to do, I'm substituting them, these amounts, the initials, so I'm going to substitute there, which is for nitrogen gas, it was 1.2, and then for hydrogen it's 12, and initially we had no product, which is the ammonia. And then here we'll have minus x equal to, and here we'll have minus 3x because it's 3 there, and then because it's 1. And then here you have plus 2x because it's a product, right? And then we were told 5.6 of nitrogen was there at equilibrium. So it's a 5.6. I've changed it to 0.2. It's going to be 0.2, right? In order to know from this amount that you had initially and what is going to be used and what is going to remain, so you can say 1.2 minus x is equal to 0.2. So that will give us 1. It's 1.2 minus x is equal to 0.2, and then the math is going to be x is equal to 1.2 minus 0.2. X is equal to 1. So the x here is what? Is 1. And then if your x is 1, and you need 3x, so you'll say 3 times 1 is going to be what? 3. So here it's going to be minus 3, which means this is 3 times this. So 1 times 3 is going to be 3. And then here, if you have x here is equal to 1 and you're looking for 2x, it's going to be 2 times 1, which is going to be 2. That will be plus 2. And then remember, I told you that when you have this amount, that means you also have this amount at equilibrium. So it's going to be what? 2 there. So now what are we going to do in order to get this amount here? So we're going to say 12 minus 3 is equal to 9. So say the amount available minus the amount used, and this is what is going to remain, which is 9. So we convert now. These are the number of moles of reactants left at equilibrium. So we converted these number of moles into concentration at equilibrium there. So we'll say 0.2 divided by, what was the volume? It's 5 dm3. It's 5 dm3 there. So we're going to say we divide by 5. 0.2 divided by 5. Let me punch quickly in the calculator. It's going to be 0.04. And then here we'll say 9 divided by 5. 9 divided by 5 is 1.8. And then here we'll say 2 divided by 5, it's 0.4. 0.4. Now the question wanted the concentrations at equilibrium. So you will say concentration of hydrogen, which is this, it's 1.8 mole per dm3. And then you say concentration of nitrogen at equilibrium is equal to this amount. It's 0.04 mole per dm3, right? Now let's continue with the questions. Now at 6.3 it says calculate the equilibrium constant. So now that you have the concentration at equilibrium, you can calculate, this is 6.3, you can calculate Kc by saying concentration of product, the product which is ammonia to the power 2 divided by the concentration of nitrogen times by the concentration of hydrogen. Hydrogen is to the power 3. So to the power 3, so it will be the concentration at equilibrium of ammonia is 0.4 square divided by the concentration of nitrogen. Nitrogen it's 0.04, and then times by the concentration of hydrogen, which is 1.8, 1.8 cube. So when you punch that in the calculator, it will give us the Kc value, which is 0.69. 0.69. I hope that makes sense. And then now 6.4, it says how will the yield of ammonia change if a smaller container than 5 dm3 is used? So if the volume, this volume is what is changed. So if the volume is changed, that means the pressure changes, right? That means the pressure changes. So if the pressure changes, how does the pressure changes? The volume and the pressure are inversely proportional. So if the volume has been decreased, it says smaller container has been decreased the volume, that means the pressure has been increased. So increase in pressure, what does it do? It favors the side with the least number of moles. So the least number of moles is this side, right? So increase in pressure favors the side with the least number of moles. It's 2 moles, it's 3 plus 1, it's 4. So it's 4 in this side and it's 2 in this side. So it will favor the side with the least number of moles. So they're asking what's going to happen in this one. So if it favors the side with the least number of moles, that means the concentration of that will increase. So the answer here is increase. The answer here is increase, right? Now it says the temperature of this reaction increases from 573 to 700 Kelvin. Now this new temperature, the equilibrium constant for this reaction decreases. So we know when the temperature increases, it favors what? Endothermic reaction, right? So, but if the Kc decreases, that means that the forward reaction is not favored here, because if the Kc, remember Kc, if the Kc decreases, that means the concentration of products decreases. That means it's the reverse that is favored. And then the forward reaction here is exothermic. Now the 6.5 are they asking, is the forward reaction exothermic? The forward is definitely exothermic because the concentration of product here decreases due to the decrease of Kc that we are told, and also because the temperature increases favors the endo, which is the favor of the endo is the reverse. We see by the Kc decreases because it favors the reverse. Now in 6.6 it says explain your answer. One of the very important thing when you explain this, guys, it's very important. 6.4, let me write it here. So what is important here? What is important here, guys? You will say here, the first thing you will say, the increase in temperature favors endothermic reaction. That's the important point there. And then you say the reverse reaction is favored. Reverse reaction is favored. So if the reverse reaction is favored, that means the concentration of the reactants is going to increase. So you say the concentration of hydrogen and concentration of nitrogen increases, and then the concentration of the product, which is the ammonia, decreases. That's why our Kc decreases, because it's the reverse that is favored and it's the endothermic that is favored, the concentration of product and the concentration of reactants. The concentration of product decreases and the concentration of reactant increases. I hope that makes sense. Cheers, bye.